Welcome to this lecture series in real analysis. In this lecture, we'll talk about the cardinality of the set of all the continuous functions on the real line, and let us recall some relevant things. So obviously, we will need to know what is meant by continuous functions, and we have discussed various criterions about them, so all of this one should be familiar with by now. And we need to know that the rationals are dense in R. This is something that we proved way earlier in the course. And we need to know this fact that the cardinality of the set of all the maps from rationals to reals is same as the cardinality of the set of all the reals. And this should be immediate to you if you've been solving the exercises I have been posing. But I have written down a proof here. Okay. Here are some problems for practice. And now let us get started. So first we will prove a nice fact about, you could say, extensions of continuous functions. So suppose f and g are two continuous functions which agree on a dense set. So there is a dense subset A of R such that the restriction of f to A is same as the restriction of g to A. So they agree on a dense set. Then they are equal. So the continuity assumption is of course very, very important here. Without that, this lemma cannot be true. So if two continuous functions agree on a dense set, then the two continuous functions agree everywhere. That is the thing. And the proof is very simple. We will use the convergence criterion of continuity. So let x naught be an arbitrary real. And we want to show that this is the case. That's what it means to say that f and g are equal. Okay, so here is the main idea, or the main point, if you will. So since A is dense, or let me write it in a different way. So A is dense in R, of course. Let me just say A is dense. Implies that there exists a sequence in A such that this thing converges to the point. So why is this? If you have a dense set, then one way to see it is that its closure is the entire set of reals, and that implies this. Or you could give a more hands-on basic argument. So just observe this fact that if A is dense, then any point in the real line can be converged to by points in A, right? So this is what we keep saying, that every real number can be approximated arbitrarily well by rational numbers. That's exactly what it means to say that the rationals are dense. You can come closer and closer to any real number while staying in the dense set. Okay, so we have that. And now, since xn converges to x naught, we have fxn converges to fx naught and gxn converges to gx naught, because f and g are continuous functions. But xn is in A, and therefore fn and gn are equal. So the sequences are equal, but their converging points therefore cannot be different. So fx naught is equal to gx naught. Very simple piece of reasoning, but make sure you follow everything. Okay? So let's proceed. Oops. Yeah. So let's have this notation nailed down. We make a fancy C, and then we put R inside the bracket to mean the set of all the continuous functions from reals to reals. So this is the set of all the functions from reals to reals which are continuous everywhere. And this is what we want to show, that the cardinality of this set is the same as that of real numbers. And when I first learned it, this was a bit of a surprise to me, because this seems like a lot bigger set, right? If you have the set of all the real numbers, you can create so many continuous functions. Like, it's just to me it seemed that maybe it should be more than the cardinality of reals, but it isn't. It is the same. And the proof is also very, very simple. So define a map from this set to this set, which is the set of all the maps from rationals to reals. Call this map phi. And what is the map? The map is take a continuous function to its restriction to rationals. And by the previous proposition, this is an injective map. Okay? So this is injective simply because if two continuous functions agree on a dense set, then the continuous functions are equal. This is what the previous proposition was. So this is an injective map immediately from the previous proposition. So therefore, what we see is that this cardinality is at most, which is same as the cardinality of reals as we commented in the beginning. So now the point is to show that this is at least the same as that of real numbers. Okay, but that is obvious because the constant functions are continuous. So for the reverse direction, you may want to, if you want to be completely formal, just throw this map, call it psi, and it takes a real number, maybe a, to psi sub a, where what is psi sub a? Psi sub a takes everything to a. So all we are doing is, for a real number a, just define the function which takes the value a everywhere. And that is what we associate to this point. And this is also an injective map. So the reverse thing also happens. So psi is injective. And thus we have the reverse thing. And now this is, these two things together with the Cantor-Schroeder-Bernstein theorem now deduce our desired theorem. So I should have recalled the Cantor-Schroeder-Bernstein theorem, but you can look it up in the playlist of this lecture series if you have forgotten. It just says that if there is an injection from a set A to a set B, if there is an injection from a set A to a set B and an injection in the other direction, then there is a bijection between A and B. That is all. So here we constructed an injection between this and that, but this is as a set bijective to reals. So there is an injection from here to reals, and this constructs an injection in the other direction, and therefore these two sets, the set of continuous functions and the set of real numbers, are in bijection with each other. That's it. So that's a very nice thing that we learned, and with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.